Our next test that we want to talk about here is a one sample means test, one sample t-test. So let's go right here and do one sample t-test. And this, we'll put a note here, quantitative. So it's one sample, meaning one variable. It's a quantitative test, so we're going to test one mean. That's what we got going on. The first thing we did was we talked about when to use it. And let's see just how we wrote that last one so we can be very consistent in our notes on how we're talking about this. When to use. We read we have one category variable we're testing to person a certain level. Yes. So when to use the one sample t-test. Let's do it. When to use. Okay, when do we use it? When we are testing one quantitative variable and seeing if the mean is equal to a certain value. Let's say hypothesize, that sounds better. A hypothesized, okay. So we're going to test a quantitative variable, such as like age, weight, height, I can't think of other ones. I don't know why I can think of 1,000 ones. How fast you can run a mile. All these variables right here. Anything that's quantitative. How many times do you eat out a week? How much money do you have in your bank account? Let's just do all those things right there. Any sort of quantitative variable can be tested to see if the mean of that variable is equal to a certain amount. We can test of the mean of the amount of money students have in their bank account. We can test the mean amount of time students eat out a week. It just has to be a quantitative variable. So you have to ask, like, how many times do you eat out a week? How tall are you? How high is your GPA? It's weird to say. Usually people say, what is your GPA? But it's like, how many GPA points do you have? Because it's a quantitative number. It's actual real numbers. That's what we mean by quantitative. You have to know when to use this, or else you might use the wrong test. So it would be like, let's see if students have more than $1,000 in their bank account. So we could do that test right here. We could see maybe... Let's see here. Let's do the $1,000 in the bank account. Let's see, we go out and we talk to students and see if they have more than $1,000 in their bank account. Okay, so we need first the notation that we're going to use for all this. So let's write our notation thing and make sure we have all the notation. Notation. The first thing we probably want to talk about is y bar. So we're going to need to insert some equation stuff right here. Let's go to insert equation and put in a y bar. Which one of these is the bar? There we go, y bar. Y bar is the what? That is the sample mean. So y bar is the sample mean. You know, we didn't start with our favorite one. I'm sorry. We should start with our favorite one, which is the easy one everyone knows. It's lowercase n for sample size. Sample size right here. We know what sample size is. We got it. So we got sample size and sample mean. Now we also need another sample thing. If we have a mean, we have a standard deviation. So this is sample standard deviation. It's like, hey everybody, sample standard deviation. We have that right there. Next but not least, we have mu naught. Oh, we got to get some symbols again. Let's go back to our insert equation and put in here mu naught. So we need mu and naught. And mu is going to be over here, I believe. Yes, we found the mu. Nope, we don't want the mu there. We want the mu here. And so mu and naught. There we go. Hopefully I don't forget any of the notation that we need. This is the hypothesized. If you notice the theme of this, anytime we put that little naught right there, that little O, that is the hypothesized value we're going to say the mean is. So mu naught is the hypothesized true mean. And you could say hypothesized population mean. It's just like, okay, I'm going to say that it is true that students have $1,000 in their bank account. That's just what I'm hypothesizing is true. Then we're going to test that. So that's also the tested value. Oh, I'm sorry. I just figured I'd hop online and help you guys out. This will be a video review in advance. So this is just reviewing how to do the tests. Ask questions if you got them in the chat. And I think that's the whole equation. We've done all the notation. We know when to use this now, and we're just doing every single test. And now we need a fake question. So let's do here example question. Example question. That's good. This is recorded, so definitely we got this. Example question right here. We will say, we go out and talk to 200 UT students. Classic sample size. And ask them how much money It's a very personal question to be asking people. Apparently, we're just going out. Hopefully, there's no sample bias or response bias or non-response bias, but we'll ignore the possible biases that would probably go into asking a question like this. So this is just a hypothetical theoretical problem, and let's give it a shot here. From here, let's see here. $2, oh no. In the sample, it is, let's say this, the distribution is very, let's say right skew, with a mean of, I'm trying to think of the math as we do this. I'm working the math in my head. Okay, I got it. 1,000, there we go. Let's do that. And a standard deviation of, I'm literally trying to solve this as we do this to see if I can get us to some pretty decent values. Okay, so let's do this. Let's say a standard deviation of 700. Cool, this will be pretty interesting. I think this should turn out to a t of like, I'm trying to do it in my head, but I think it's gonna be a t of about, my brain is slowing down today. It's gonna be a very small t. We'll be good. It'll be a small t. Hey, what's up, Andrew? Good to see everyone here. So now we have all the values I've been mentioning previously. Is there evidence to suggest that UT students have $1,000 on average in their bank account? Let's change the wording a little bit. Is there evidence to suggest that the true mean of students' bank accounts is equal or not equal to, there we go, I like this. Okay, so usually we want to word this for the alternative, there it is. It should have an apostrophe at the end of that. I can't grammar. So, because students have bank accounts, there we go. So the standard deviation is so big, yes, but remember, we actually need, and we should add an extra notation right here, we actually need the standard error of, and I'm gonna need the little thing right here, a notation thing that we should possibly know. I'm gonna have to do it as a thing. So we go to insert equation, and we remember these little things as we do it. Let's go first one. There we go. SE y bar. So what is SE y bar? That is equal to the standard error of the sample mean, which is s over square root of n. That is s over square root of n, so let's insert an equation here. This is solved by the equation s over square root of n. Oops. So remember, we're doing s over square root of n right now, and you'll see this in the equation in just a moment here. But this is the standard error of the sample mean, and that's all that good stuff right here. There, we got it. We have all of our notation. We're pretty good to go. If you notice, I'm trying to write out everything you would need to know for this. And so we just have an example problem right here. We have the notation we're going to be using for this problem. So hopefully we can identify it. I'm going to try to mention the conditions this time. Conditions are kind of their own thing. They're very important, but checking them is usually just kind of rote once we get used to doing these problems. So let's give it a shot right here and see if we can identify the notation in this problem. So pause the screen if you want and see if you can identify all the notation I've listed out right here. So we have right here, 200 is the sample size, kind of classic sample size for all these problems we'll probably be doing today. Let's hop over here to where we can write 200 on the screen. And so we go and we write 200 is equal to n. That is the sample size. And then we have right here the mean is equal to this. Well, that is the sample mean because that came from a sample. So that is from my sample because that's from the 200 students. I also mentioned that the distribution is right skewed. That'll come into play. And I hope you can see there's a bar above that y. That is y bar. It's not just y. Y would be an observation, but y bar is the mean for the y variable. So anytime you put a bar above it, x bar is mean of variable x, y bar is mean of variable y. You could do t bar, mean of variable named t. So a standard deviation of 700, that's going to be s, little lowercase s right there, the best I can draw. And then we want to see if the value of the rank accounts is equal to 1,000. That is the hypothesized amount right there. We can do a little better mu than that. There is our mu. There we go. So we have the different values. But watch this. We can get the standard error. the standard error is going to be s over square root of n. So we need to do 700 over square root of 200. And 700 over square root of 200 is going to be 200 square root. You have to do it this way on this calculator. Where did we lose our thing to? And now 700 over square root of this, 49. Cool. I like that. That's going to be, now I can already tell you the z-score. The z-score is almost exactly, it's about 0.61, I believe. The z-score is 0.61. You'll see that here in just a little bit. If you are following along really well, you'll be like, I see how he did that, because I actually just solved most of the equation. We'll tell you more on that in a moment. 0.4950. The next two digits round up because it's 497. So with this in mind, we have the standard error. So this is the standard error of y bar. And we can use that here in a moment. But we've taken and we've done all the notation. So now we need to go and we need to grab our steps. Let's go back all the way to the top, make sure we have all of the steps. So let's take our 4 steps and let's practice. You ready? Big brain. Okay, let's do all the steps right here. Okay, so write out the null and alternative hypotheses. Write out the null and alternative hypotheses. Okay, we are testing the mean. Always look at these equations and see what it says we're testing. It says, is there evidence to suggest that the true mean, I know I'm looking at mu now, of students' bank accounts is not equal to this right here. So I have not equals to. That's telling me the alternative right there. So all these things I've highlighted are very important for what we're solving. And I've kind of boiled these problems down to where there's no like fake info. I hate those problems. Yep, we have mu right there. Good job. The null hypothesis is that the true mean is equal to it, and you got it. Perfect answer in the chat. Great job. We have here the null states that the true mean of students' bank accounts is equal to $1,000. The alternative states that the true mean of students' bank accounts is equal to, oh my gosh, not equal to, there we go. I was back doing the null again in my head. There we go. We've got the null, we've got the alternative. The null states that the true mean of bank accounts is equal to 1,000. Great job in the chat. And the alternative states that the true mean of students' bank accounts is not equal to. Please do not make this error, which I often see. One, I see this error a lot of times. I see where people just write this. The null states equals 1,000. Make sure to tell me what equals 1,000. The true mean of money in students' bank accounts. Make sure to not make this mistake. A proportion can't be $1,000 because a proportion is a value contained between 0 and 1. So if you write proportion, be like, that's a problem. Question in the chat? Any questions, feel free to ask them as we walk through all of these steps right here. But we have here, this would be a mistake. Let's make sure we know that we want to do the true mean is equal to 1,000. And the alternative would be the true mean is equal to the true mean is not equal to. Awesome. And I hope this helps. I hope this helps everyone out. I want these videos, I might chop them up a little bit, but I want everyone to be able to watch these and to be able to understand how to do each step. So this is out to all Stats 1 students, so that way you can practice doing this and know when to use each test. So I'm going to do the next 2 after this. So perform the calculations for the z, the t, or the chi-squareds. Also check conditions. My students should know condition 1, and right then they say random. That means we randomly selected these, and I might not have said that in my problem. 200, let's just fix that. It's not going to move it. It didn't move it. So mine would fail the condition because I didn't say it was random. So make sure your problem states that they're random. We should talk to random people. You don't want to just go talk to the first 200 people. That would be a convenience sample. So oops. And if on the test it doesn't say random, probably means you failed the condition. We're usually more careful. These are just questions off the top of my head. But we would not pass the randomness condition here because the question does not state that they are randomly selected. I would probably say that on the test. Like, the question does not state that students are randomly selected, so that seems to be an issue, and we do not know for certain they're randomly selected. This is a problem with the test. Condition 2. Condition 2 is 10%, as in we need to select less than 10% of the population. So it's pretty clear that 200 students is less than 10% of all UT. UT has something like, I think, I'm going to probably quote a wrong number, 20,000 undergrad, let's just say that. And I know we have more than 2,000 undergrad, so 200 is way less than 10% of all UT students. So 200 is less than 10% of all UT students, we pass. And then the last condition for this is nearly normal. If you notice, I highlighted that the distribution is skewed to the right. That's because there's probably some students with very large bank accounts like this. So you could say 1,000 is here, or I'm trying to think where 1,000 would be at. It'd probably be over here because it's a right skew distribution, or maybe a little further over. But wherever it is at, it does have a right skew to it. We see that the distribution is skewed to the right. There's a lot of people with lower bank accounts, and then there's this heavy right skew where we see some students with very, very high bank accounts. So with that in mind, do we pass the nearly normal condition? The answer is yes, we do. Because although the original distribution is skewed to the right, it could look something like this right here. The distribution of the mean will be normal, more normal, and tighter the larger n gets. So that blue distribution I've drawn right there is the distribution of the mean, and of sample size of 200 should be large enough that the distribution of the mean will be more normal and tighter and nearly normal enough. We're not concerned so much of the first distribution I drew, the black one in the background. We're concerned about the distribution of the mean, which will actually follow the rules of the central limit theorem, that it'll be more normal and tighter. And you know, if you remember back how it gets tighter, it's by n. As n gets larger, that gets smaller. That's it getting tighter right there by the standard error. And then the more normal is when I draw the blue distribution looking more normal. So it's not that the black distribution ever becomes normal. It's that the distribution of the mean should be nearly normal. So all that key stuff right there. We do seem to pass the nearly normal condition because 200 is large enough to make the distribution of the mean be nearly normal, even though this is right skewed. So we pass all our conditions. Now we just have to know the equation, but great stuff for us. We don't have to know it. It'll be given to us. So let's go ahead and write out the equation. Let's go to Insert, Equation, and we're going to solve for t with n-1 degrees of freedom. T with n-1. We won't need the pen for a little bit here. So let's go to Equation. We're an equation builder, aren't we? We are. Where'd my equation go? Insert, there we are. Equation, can't do an equation inside equation. Okay, so we need t with n-1 degrees of freedom. Okay, there we go. T with n-1 degrees of freedom. That subscript right there is the degrees of freedom. And now we're going to go equals, and after the equals, we're going to put our equation. So let's go right here and put the bottom part of it, which is going to be s over square root of n. So we need to first do this. And let's go here, and let's do that. And s over square root of n, if you notice I solved that earlier, and this will be y bar minus mu naught, so we need a little y bar right here. Let's put our y bar, which is the sample mean, minus mu naught, which is the hypothesized mean, the hypothesized true mean, technically. So we're going to put a mu naught right here. There's the mu, there's the naught, and we got it. We have now written our equation, and once we click outside of here and click over, it's going to make it small. But we're going to copy paste this equation, put them side by side, and show how the equation is solved. Now, please note, I already kind of did some of the work for this, because since the problem gave it to me, I went ahead and solved for the standard error. The standard error was 49.50. And if you're wondering how I did that, it was just s over square root of n, which we saw previously was 700 over the square root of 200. That is s, which is the standard deviation, over the square root of the sample size. So 700, which would be right here, over square root of 200 equals to 49.50. Now I'm simply going to take the difference between the two. The difference between the two is going to be 1030, which is my observed sample mean, observation minus mean of what we would expect. And if you notice, the difference is 30. This was the math I was doing in my head earlier in the question. I said, what's 30 divided by 50? Oh, that's 0.6. Well, because it's 49.50, it's going to be about I believe I said 0.61. Let's see how close I was with my guesstimate of this. Well, there's our standard deviation. Let's carry all decimal place accuracy with it. And Brian said it would be, it's 30, I knew that. But let's see, I said 0.61, the answer is and it rounds to 0.61. We did it. It's 0.606, but it rounds to 0.61. So you know what? I'm taking the win on that. I'm going here and I'm writing 0.61. That's what I said it would be, and what is this n-1? Those are the degrees of freedom. So let's add in the degrees of freedom here. That is a t-statistic with 199 degrees of freedom. That is a subscript. Do not multiply those numbers. Stop. Don't multiply those numbers. That is a subscript. And you might just delete that off now so there's no confusion. So it is equal to 0.61, but there are 199 degrees of freedom. So you know what? We forgot one thing on our notation. Our last thing on the notation should be df equals degrees of freedom. And that is n minus 1. Every t will have with it degrees of freedom. I forgot those degrees of freedom in our notation. So sorry if you've been going down through the problem, but these are all the notations right here, and now I've moved the text. But the degrees of freedom, df stands for degrees of freedom, and for this test it is n minus 1. Watch out, let's put a note, for this test. Let's put an exclamation point right there. Only for this test, the one sample t-test is n minus 1 degrees of freedom. Very important stuff right there, and oh no, we're gonna make the notes all crazy if we leave this in, so we can't. Let's do this. Let's go down here and write out that down here. Okay, so let's put it right here, make this look all nice, and let's go df equals degrees of freedom n minus 1, and then put a star for this test. Only for this test is it n minus 1. And why? It's a one sample t-test, and there's a lot of theory behind it. I'm not going to do that right now, but I can tell you why. It's because of the estimates for the mean, but we won't go into that right now. But for your knowledge, a one sample t-test has how many degrees of freedom? N minus 1. A one sample t-test has n minus 1 degrees of freedom. Nice and easy to remember that one. Find the p-value. Well, we got the t-statistic. Here's the thing. We can't know this exactly, but I can give you a pretty good guess of it. And this one I'm going to be pretty good on the guess on the p-value. Here's what we got. Is we've got our curve. And with enough degrees of freedom, people in my class might know, with enough degrees of freedom, the t is basically the what? With enough degrees of freedom, the t is basically the what? And what is enough degrees of freedom? Usually about 60. The t is basically the z. The t is basically the z. So it's never exactly the z. The t, we talked about it earlier, becomes more like the z. Remember, Mr. T comes in and says, smashes it down, and then it rises back up. It's probably the worst Mr. T impression ever. I still want to make videos with him if he's ever like, hey, I want to make some stats videos. Like, yes, dream come true. But, because we all love him in statistics for his t distribution. But it's basically the normal. It's a more exact calculation created by William Gossett, who Ronald Fisher wouldn't publish his work, and so he used the pseudonym student T to get the t distribution published. So it's a more exact curve that takes into account smaller sample sizes based on the degrees of freedom, and standard deviations and other stuff for other tests like two-sample t-test. This one only takes into account sample size. So what do we have going on right here? We need to find the p-value. That's the whole goal of this. We need to find the p-value by plotting it. Now this one's going to be tricky. How are we going to find this p-value? Step 3, find the p-value. Well, I need to plot that, okay? Okay, so I'm going to go here. I'm going to plot right here at 0.61. Now be careful. You're almost done. When you do this, make sure to shade according to the alternative. What way am I going to shade? What way will I shade my alternative? I'll shade my alternative. This points to the right, and that points to the left. So I'll shade both sides. I'll shade both sides. That's what I'll do because it's the two-sided test. This is the does not equals test. So I'm going to draw a line right here that is just as extreme on the other side at negative 0.61. So because the alternative is a two-sided, if it was one-sided, I would just shade to the right that way. If it was left, I would shade to the left, less than. But since it's two-sided, I shade to both sides. So we go here and we shade our p-value. And I know you might be thinking, I can't figure out that p-value. Does it look like I've shaded more than 5% of the curve? These are the kinds of test questions we really like here because the program will tell you the exact p-value. And I'm going to try to take a good guess at this here in a moment. Oh, why not? I'm going to guess that this p-value is 0.57. That's my guess of the p-value. 0.572. 0.572. And I'll tell you if I got close how I knew. Oh, no, wait. Oh, I can't. No, I'm going to guess 0.18. That's a 1 right there. I swear the video is not edited. 0.518. And I'm trying to think. Maybe statisticians watching this be like, I know why he's guessing that. There's some numbers, and I can't for the life of me think up the one number, but let's find out the p-value. I can no longer use the z-curve. I'm not using the z, I'm using the t, and it looks virtually identical. You'll notice things about this, that as you increase the degrees of freedom, you're basically getting the z-score, but when you decrease it, it starts to get smashed down. Smash down, rise up into the normal. The more degrees of freedom, the more availability it has to be normal. So what did we get? We got a t of 0.61. We're not done though, because we have to put in our degrees of freedom. Oh, sorry, that's degrees of freedom. Degrees of freedom were 199 because the sample size was 200. We got a t-score of 0.61. And what is our p-value? Oh, it's close. I was thinking of the interquartile range z-score, so don't worry about that. Little side note of why I was guessing it. I should have went with my other guesses. I think I had some guesses closer to that. But the p-value is 0.543. But I want you to look at that graphic, and I want you to look at my graphic. So I want you to think, how similar does my graphic look to this one? It doesn't look perfectly like it, but it looks a lot like it. And I think it was 0.543, so let's put in the exact p-value right here. I didn't know when I made up this problem that it would come out to almost that score, but that was kind of nice. And so that, I believe, we'll double check the value because we want to be exact. We want to put the real p-value, not close to it. Yep, 0.543. That is the area shaded outside the curve. That is the area under this curve here on the right and to the left of it, below negative 0.61 and above positive 0.61. If I shade to the right, what would the p-value be? Well, maybe this could be a test question. All you would do for the right-tailed test is take this right here and do what to it to just get the greater than test? Take this and divide it by 2. 0.272 if it rounds. Let's see what it rounds to. 0.272. And it rounded down. There might be some decimals we're not seeing, but if you notice the two-tailed test is simply double, and there's just some decimals we're probably not seeing, or it's annotating decimals because there might be a 5 after that. But it's just half of it. How about if I go below this? What should the area be below that line? Well, this is good practice. The area below that would be 1 minus that area. So that will be 0.72, and let's see if it says 9 or 8. It'll be one of those two. 0.729. So that one rounds up to 0.729. So all that's going on right here is we're just seeing how the different p-values are calculated. This is the less than test because it shades below where we landed. This is the greater than test because it shades above where we landed. And this is the two-tailed test because it reflects the area on the other side where we landed. So make sure you know that when you have a greater than test, you shade to the right. When you have a less than test, you shade to the left. And when you have a two-tailed test, you reflect the smaller area on both sides. P-values can only be between 0 and 1. If you get one bigger than 1, you've done something wrong. Well, we're basically done with the problem. I've got the p-value, and if we gave this to you on a test, you might say, wait, I can't figure it out. That's definitely more than 50% or 0.5% of the curve shade, or 5%, excuse me. That's definitely more than 5% of the curve shade. That is a very large p-value. Either way, just when you draw it out there and you look at it, that is a very large p-value. So what do? Well, we just need to state our conclusion. We are going to say, I fail to reject the null. I fail to reject the null that the true mean of student bank accounts, I did it again, I don't know how to grammar, is equal to, this means I did not have evidence the true mean of students' bank accounts, we're going for all the points on the test, is not equal to. What does this actually mean? Like, what are we stats people saying with this? It just means it's believable that the true mean is $1,000. And that's not an individual student having $1,000. It's like on average, students have $1,000. Apparently, due to this fake problem right here, it's a believable claim because we did not land far enough away. Think about what kind of evidence would lead us to rejecting the null. What if I spoke to these 200 students and they had on average $50,000 in their bank accounts? You might be like, that sounds like good evidence. What if they had exactly 1,000 as their mean? Well, then we'd land right here again, and that would lead to the highest p-value. In this instance, if we landed there on the two-tailed test, the p-value would be 1 telling us that is the most likely thing to see if the null is true. And just think about that. The most likely thing to see if the null is true is $1,000. And if we landed there, we would say, well, yeah, I guess the null is pretty believable. We're not saying the null is true. Do not use those bad A words. Do not say that except word. Don't say that. We would just say, I continue to believe the null, or I do not reject the null. I fail to reject the null. So continuing to believe is fine. We're not going to state the null is true. We're not going to say we've proven anything. We're just going to say we have evidence for the alternative, or we did not find evidence. Very big stuff on the wording right there that you're hearing me use. You won't hear me, hopefully, say words like I've proven this, or I know this. In statistics, we're science-based, so we say I have evidence, or I did not find evidence. So that's what we have going right there. And you should know which of the claims is the evidence-based. The alternative is the evidence-based. The null can be anything. We start out with a null, we test it, and then we see if we have evidence for the alternative, which would lead us to reject the null. If there's evidence for the alternative, we reject the null. If we don't have evidence for the alternative, it's because we cannot reject the null.